The muddy runway at Buna Airfield stretched out before him like a graveyard of twisted metal and shattered dreams. February 24, 1943, New Guinea. Lieutenant Clyde Gessel stepped out into the suffocating heat and stared at what the Australian infantry had dragged from the jungle. 5 Japanese fighters, their frames bent and broken. Their secret still somehow intact enough to kill Allied pilots day after day. For months now, American P-40 Warhawks and British Hurricanes had been torn apart in the skies by nimble enemy aircraft that seemed to defy the laws of physics itself. Double Immelmans, hammer headstalls, maneuvers that shouldn't have been possible. Everyone called them Zeros, but Gessel knew better. These weren't the carrier fighters from Pearl Harbor. These were something different, something the Allies didn't fully understand. Looking at the twisted remains scattered across the runway, he saw possibility. Enough salvageable pieces to rebuild one complete aircraft if they were careful. An engine cowling here, wings there, control surfaces from another wreck. What Allied intelligence had dismissed as primitive copies of Western designs, Gessel suspected might actually be engineering masterpieces built on completely different principles altogether. 6 months later, inside Hangar 7 at Eagle Farm Air Base, test pilot Bill Farrier would climb into the cockpit of this resurrected enemy fighter. What he would discover would overturn everything the Allies believed about Japanese air superiority. The mystery aircraft wasn't merely maneuverable, it was something far more dangerous and far more fragile than anyone had imagined. Port Moresby was already heating up past 90 degrees when Gessel stepped off the C-47 transport that morning. His boots hit the coral dust runway with the measured precision of a career engineer. February 24, 1943, had begun like any other day in the Pacific Theater. Radio chatter about Japanese raids, mechanics swearing over damaged Allied fighters. Another stack of combat reports that made no tactical sense whatsoever. Then the telegram from the Australian infantry had changed everything. 43 words that shifted his entire mission. Buna Airfield. Multiple Japanese aircraft wrecks recovered. Request immediate technical evaluation. Possible new fighter type. Gessel had examined enough mangled aircraft to fill a scrapyard, but this felt different. Since October, when he'd been assigned as enemy equipment engineer for the Allied Technical Air Intelligence Unit, every crashed Japanese fighter had been labeled identically in official reports. Zero type. Origin unknown. Capabilities classified. The simplicity frustrated him. An engineer understood that aircraft design revealed everything. Enemy doctrine, manufacturing capability, strategic thinking. You couldn't fight an opponent by giving everything they flew the same designation. The jeep ride to Buna took 3 hours through jungle roads that barely qualified as such. Burned-out pillboxes passed. Abandoned supply dumps marked the Japanese retreat. Gessel used the time to review combat reports from pilots across the Pacific. British Hurricane pilots over Burma described Japanese fighters that could turn inside their own turning radius. American P-40 crews in China reported enemy aircraft that climbed like angels but seemed to disintegrate after taking any significant damage. Dutch pilots in the East Indies had sent desperate radio warnings about Japanese fighters executing impossible aerobatic moves. Then the communications went silent forever. The pattern was becoming undeniable to anyone willing to see past the propaganda. These weren't the same aircraft that had attacked Pearl Harbor. The carrier-based Zeros were formidable, certainly, but they represented only one piece of Japanese air power. Intelligence suggested at least 3 different fighter types in regular combat service, each optimized for different tactical roles. Yet Allied training manuals still treated Japanese aviation as a monolithic threat, fast and maneuverable but ultimately inferior to Western engineering. That assumption was beginning to look dangerous. Buna Airfield appeared before them like a scar cut through the jungle canopy, its single runway pocked with bomb craters and littered with debris from 2 armies. Australian infantry had done their job thoroughly. 5 Japanese aircraft had been dragged clear and arranged in rough formation near the abandoned control tower. Even from a distance, Gessel could see these weren't Zeros. The wing planform was wrong. The engine cowling suggested an entirely different power plant. The fuselage proportions spoke of an aircraft designed for maximum agility rather than carrier operations. The first aircraft was the most intact, a single-seat fighter with fabric-covered control surfaces and a radial engine that looked remarkably similar to American designs. Faded olive-green camouflage still visible, distinctive red circles marking Imperial Japanese Army Air Force equipment. The landing gear had been retracted when it crashed, indicating the pilot had attempted a belly landing rather than a wheels-down emergency approach. Bullet holes stitched across the port wing showed it had been in combat when it went down. Gessel walked the wreckage line like a detective examining crime scenes. The second aircraft had taken a direct hit from what looked like 20mm cannon fire. Its engine was completely destroyed, but the cockpit and rear fuselage remained largely intact. The third had burned, leaving only basic airframe structure and a few key components that might still offer useful information. The fourth was missing everything forward of the cockpit, but its wings and control surfaces were undamaged. The fifth had suffered what appeared to be catastrophic structural failure. Both wings had folded upward in a pattern suggesting extreme G-force loading during a high-speed maneuver. Working methodically through the afternoon heat, Gessel began cataloging recoverable components: engine cowlings, propeller hubs, instrument panels, control cables, fabric samples, ammunition boxes. Each piece represented a fragment of Japanese design philosophy made tangible. The ammunition told an immediate story: 7.7mm rounds in small quantities, suggesting these fighters carried lighter armament than Allied standards. The fabric covering was high-quality linen with distinctive doping patterns indicating sophisticated manufacturing techniques. But the control surfaces revealed the real secret. Each aircraft mounted what appeared to be split flap systems that could be deployed independently during flight, not for landing configuration, but for combat maneuvering. Gessel had never seen anything like it on Western fighters. The engineering was elegant and purposeful, designed to increase lift and tighten the turning radius during air-to-air combat. It represented a fundamentally different way of thinking about aerial warfare. As the sun began setting over the jungle, Gessel made his decision. Among the 5 wrecks lay enough intact components to potentially rebuild one complete aircraft. It would require shipping everything to Brisbane, requisitioning machine shop time, and convincing skeptical superiors that reconstructing an enemy fighter was worth the enormous effort. But the alternative was continuing to fight an enemy they didn't understand, using tactics based on assumptions rather than engineering reality. The telegram he sent that evening was characteristically brief. 5 Japanese fighters recovered. Recommend immediate shipment to Eagle Farm for complete reconstruction. Preliminary analysis suggests new fighter type with unique combat capabilities. Request priority handling. 3 days later, the reply came back with authorization and a warning that would prove prophetic. Approved. But remember, understanding the enemy and defeating the enemy are 2 very different problems. Hangar 7 at Eagle Farm Air Base had never hosted a project quite like this one. Built for standard Allied maintenance operations, the cavernous space now resembled an archaeological dig crossed with a precision machine shop. Wooden crates marked enemy equipment classified filled one corner. The center floor had been cleared to accommodate the most ambitious reverse engineering project in Pacific theater history. March 15, 1943 marked the official start of what ATIU technicians privately called Project Phoenix, the resurrection of a complete Japanese fighter from scattered wreckage. Sergeant Mike Kowalski had spent 12 years maintaining aircraft for the Army Air Forces. Nothing in his experience had prepared him for rebuilding an enemy fighter without technical manuals, spare parts, or any understanding of Japanese manufacturing standards. The 5 sets of wreckage from Buna had been carefully catalogued and arranged according to aircraft systems. Engines in one area, control surfaces in another, instruments and electrical components in a third. Each piece carried a tag indicating its source aircraft and condition assessment, creating a 3-dimensional puzzle with over 2,000 individual components. The engine presented the first major challenge. The Nakajima Homare radial power plant shared obvious design heritage with American engines, but crucial differences in cylinder head design and carburetor configuration suggested the Japanese had developed their own manufacturing techniques. Kowalski's team discovered that Japanese tolerances were actually tighter than American standards in several key areas. Cylinder bore dimensions varied less than 0.03 of an inch across all 5 engines, indicating precision manufacturing that contradicted intelligence reports about primitive Japanese industrial capabilities. Working 16-hour days under harsh fluorescent lighting, the technicians began solving problems no Allied engineer had ever confronted. Japanese control cables used different wire gauge and tensioning systems than American standards. The electrical system operated on a 24-volt configuration, requiring complete rewiring with available components. Most challenging was the unique combat flap system that Gesell had identified as key to the aircraft's legendary maneuverability, a complex mechanical linkage that had to be reverse-engineered from damaged components and educated guesswork. By April, the project had consumed over 3,000 man-hours and attracted attention from high-field engineers who flew in specifically to observe the reconstruction process. The Japanese approach to weight reduction became apparent as each system came together. Where American fighters used steel components, the Japanese substituted aluminum alloys. When Allied manufacturers designed redundancy into every system, Japanese engineers stripped away anything that added even a single pound. The outcome was remarkable. An aircraft weighing just over 5,000 pounds when fully armed, nearly 2 tons less than equivalent American fighters. The combat flaps became the standout engineering achievement across the entire airframe. Controlled through a lever in the cockpit, these flaps extended to 30 degrees during tight turns, creating a massive boost to lift and dropping the stall speed dramatically. American pilots had reported witnessing Japanese fighters performing what seemed like impossible maneuvers, and now the explanation became obvious. When Japanese pilots deployed those combat flaps mid-fight, they could hold steady flight at speeds that would cause any Allied fighter to drop from the sky in an uncontrollable spin. It was sophisticated, beautiful, and utterly different from how Western engineers approached design. Lieutenant Gesell devoted considerable time examining the cockpit arrangement, which revealed much about how Japanese pilots trained and fought. The instrument panel was sparse by American standards: basic engine gauges, an attitude indicator, compass, airspeed gauge, nothing more. No radio compass, no advanced navigation systems. The gun sight was a simple bead arrangement demanding serious piloting ability to use well. Everything in that cockpit spoke to pilots expected to fly by looking out the window and defeat enemies through superior skill at the controls rather than superior technology. The weapon setup told a different story about how these two air forces thought. Two 7.7mm guns mounted in the engine cowling provided all the offensive power this aircraft carried, roughly a quarter of what a standard American fighter packed. Yet the ammunition system had been engineered for sustained shooting rather than quick bursts, suggesting pilots trained to make each shot count instead of relying on sheer volume of fire to score kills. As summer arrived, the restored fighter began taking shape as an actual flying machine. The distinctive olive-green paint scheme had been recreated from whatever paint remained on hand, though the red circles denoting Japanese Army Air Force service had been swapped for American insignias. Throughout the airframe, test equipment was installed to track engine output, structural stress, and how the controls responded during actual flight. Every system underwent multiple checks, yet serious unknowns lingered about how the aircraft would handle and what stresses it could withstand. Structural testing of the wing assemblies delivered the most worrying finding. The combat flap mechanism worked properly from an engineering standpoint, but the wings themselves displayed troubling stress patterns when subjected to simulated G-forces. Hairline fractures formed where the wings attached to the fuselage at loadings that American fighters handled without concern. The extreme lightness that granted such incredible performance created hidden weaknesses that only appeared through careful engineering investigation. By late July, the project neared completion, but the finished aircraft posed as many mysteries as it answered. The projected performance was clearly exceptional. Calculations suggested speed and turning abilities surpassing any Allied fighter below 20,000 feet. Yet those same design decisions creating this performance also built in structural constraints that could become deadly in actual combat. The aircraft could fly, but whether it could endure the severe maneuvering that made it legendary remained uncertain. Test pilot Bill Farrier touched down at Eagle Farm on August the 10th with instructions to run the most hazardous flight evaluation of his professional life. The rebuilt Japanese fighter represented months of exhausting effort and considerable resources. More than that, though, it carried the weight of expectations from Allied airmen needing answers about their enemy's capabilities. Walking the aircraft's perimeter for his pre-flight check, Farrier confronted a choice. This was either the answer to understanding Japanese air superiority or the most sophisticated death trap ever constructed in an Australian hangar. August 17th arrived with clear skies and stillness over Brisbane, visibility stretching to the horizon and barely a breath of wind. Ideal for what would become the Pacific's most dangerous test flight in the entire war. Farrier had invested the previous 72 hours absorbing every technical drawing, every structural report, and every engineering record from the project. Though no amount of paperwork could truly prepare him for climbing into an enemy fighter's seat. At 0730, he started his methodical pre-flight walk-around, the same deliberate approach that had brought him safely through dozens of experimental aircraft tests. The restored K-43 rested on the tarmac like something from another world, its olive-green finish and unfamiliar shape making it unmistakably foreign compared to any Allied machine. Farrier moved systematically around the aircraft, verifying control surfaces moved freely, engine panels were secure, and landing gear functioned properly. The control surfaces, covered in fabric, felt firm beneath his fingers, but disturbing in their lightness compared to the metal he knew. All components had been rebuilt, according to Japanese specifications, but using whatever materials and techniques American factories had available, raising questions about whether tolerances matched the original design. The cockpit intensified that sensation of entering an alien landscape. Instrument placements seemed wrong, engine readouts where he didn't expect them, stick and rudder pedals positioned differently than every American aircraft he'd flown. Most striking was the complete lack of any armor, no reinforced windscreen, no back protection, nothing shielding vital systems. Japanese airmen apparently accepted that lack of protection as the cost of maximum performance, a choice fundamentally at odds with how Allied fighters were built. Engine start at 0800 went smoothly. The Nakajima engine settled into a steady rhythm that sounded not entirely unfamiliar. As Farrier increased throttle for his run-up checks, differences became apparent. The engine jumped at throttle movements faster than expected, while heating the carburetor produced temperature swings pointing to different internal airflow design. Each system required getting used to its own peculiar behavior. Early taxi tests hinted at something unusual about how the aircraft handled. The light construction made it extremely sensitive to control inputs, the smallest rudder pressure causing immediate directional shifts needing constant correction just to taxi straight. Ground handling suggested an aircraft needing pilots with many hours in type, not the adaptability emphasis of Allied training. Takeoff at 0815 showed exactly what Allied intelligence had underestimated. The K-43 became airborne after rolling less than 800 feet, climbing at over 2,000 feet per minute initially. Within 3 minutes, Farrier had reached 8,000 feet, a climb rate surpassing every Allied fighter in operation. Yet that same construction creating this climb also funneled every air bump straight to the pilot, producing a sensation closer to riding a bicycle than commanding a military machine. At 8,000 feet, level flight exposed the aircraft's greatest strength alongside its most serious trouble. Cruising at 75% power showed roughly 280 miles per hour. Respectable, nothing remarkable for Americans. But the moment Farrier extended the combat flaps and pointed into a mock dogfight, the aircraft transformed. Flaps down 30 degrees, the K-43 maintained controlled flight below 90 miles per hour while executing turning circles that seemed to violate basic aerodynamics. The combat flap system changed everything so completely, it felt like flying a different aircraft entirely. Stalling characteristics simply vanished, replaced by gentle mushing that allowed constant turning at angles of attack that would spin any American fighter into a fatal dive. Turn diameters shrank to under 800 feet while staying in positive G loading, creating combat moves Allied pilots had thought impossible. American intelligence now finally understood how Japanese flyers achieved their reputation. Extended maneuvering at these extreme conditions, however, started showing the structural problems earlier analysis had foreseen. During high-G pullouts mimicking diving attacks, vibrations through the control stick signaled airframe strain beyond what it was designed for. Visible wing bending occurred during maximum rate turns, and fabric wrinkles across the control surfaces pointed to structural distortion. Those same features enabling extraordinary turning also contained the seeds of failure when pushed hard. Mock dogfights with squadron leader James Mackenzie's Spitfire revealed both advantages and weaknesses of the rebuilt fighter. Below 15,000 feet, the K-43 could outturn the Spitfire so drastically that Mackenzie couldn't get into firing position during turning fights. But whenever Farrier pushed those turning advantages to their limits through aggressive high-G maneuvering, structural restrictions forced him to ease back or risk breaking apart. The most striking moment came during a head-on pass when Farrier pulled maximum G to dodge Mackenzie's simulated fire. Initially, the aircraft responded, but around 4.5 Gs, alarming groaning from the wing roots forced immediate reduction and maneuver termination. Post-flight inspection uncovered stress cracks in wing fittings exactly where engineers had predicted problems would show themselves during actual combat. Landing revealed more about the Japanese approach. The K-43 touched down at under 70 miles per hour and stopped in less than 600 feet, enabling use from rough airstrips impossible for Allied aircraft. Yet landing required continuous control input to prevent a ground loop, and the light construction left it vulnerable to crosswinds that robust Allied designs shrugged off. Farrier's final report captured the fundamental paradox of Japanese fighter design. Stunning performance achieved by abandoning the structural safety margins Allied engineers treated as sacred. The K-43 could perform maneuvers Allied pilots considered impossible, yet did so by flying dangerously close to structural breaking points that no American aircraft would be allowed to approach. In Farrier's unforgettable description, it was like flying a paper airplane, incredibly nimble, but prone to tearing apart under the kind of beating Allied fighters were built to withstand routinely. A transport carrying the restored K-43 landed at Wright Field on September 23, 1943, launching the most thorough evaluation of an enemy aircraft the American military had ever undertaken. Colonel Harold Watson, leading the USF Test Training Unit, had gathered test pilots and engineers to extract every possible tactical lesson from what intelligence had now confirmed as the Nakajima K-43 Oscar, the mystery fighter that had been ripping through Allied squadrons across the Pacific for nearly 2 years. Wright Field offered testing resources representing American aviation's absolute peak: wind tunnels, structural labs, measurement tools surpassing anything available in the Pacific. The Oscar would face evaluation so complete it would expose not only what it could do, but the entire thinking behind Japanese air power. Major Robert Strobel, the field's senior test pilot, brought analytical rigor to the project, the same precision making Wright Field Aviation's premier testing location. Initial testing concentrated on fundamental performance, establishing exact numbers for top speed, climbability, ceiling, and range. Strobel's early flights confirmed what Farrier had observed about remarkable climb potential. The Oscar climbed to 20,000 feet in just 8 minutes, reaching an altitude that would have taken the vaunted P-51 Mustang nearly twice that time. At its optimal altitude, the aircraft achieved a maximum speed of 308 miles per hour. Respectable performance, certainly, but nothing that set it apart from other Allied fighters of the era. Yet these measurements told only part of the story. The true significance of this aircraft lay somewhere deeper, hidden in the engineering choices that gave it its fearsome reputation. When engineers examined the airframe in detail, they discovered the remarkable compromises that had been made in pursuit of agility. The entire structure weighed just 3,200 pounds when empty, a full 1,500 pounds lighter than comparable American fighters. Japanese designers had achieved this dramatic weight reduction through ruthless elimination of every component they deemed expendable. Protection for pilots, self-sealing tanks that could withstand battle damage, backup systems for critical controls, structural reinforcements that other nations considered mandatory. All of it had been stripped away or minimized. The result was an aircraft perpetually balanced between two opposing forces, the desire for raw performance and the need for basic survivability. Scientists working in a wind tunnel with 7 by 10-foot dimensions began documenting something truly remarkable. They were analyzing the Oscar's unique combat flap system, a feature that would explain so much about how these aircraft fought. When pilots deployed those butterfly flaps during tight turns, the wing's lifting capacity increased by 37%. More impressively, the airflow remained attached to the wing at angles where conventional designs would simply stop flying. This innovation let Japanese pilots execute turning maneuvers at speeds where American pilots would have expected nothing but a deadly stall. Western aeronautical engineers had never explored this approach with real seriousness. Yet here it was, embodied in production aircraft. It was brilliant until one examined it more closely. The same testing that confirmed the flap system's effectiveness also revealed its fatal flaw. Once airspeed exceeded 250 miles per hour, deployment of those flaps subjected the wings to stresses that pushed far beyond what the design could safely tolerate. The system excelled at low-speed dogfighting, but became dangerous, even catastrophic, at higher speeds. Japanese pilots faced a constant tactical calculation, sacrifice maneuverability for structural safety, or maintain agility and risk catastrophic failure. Examination of the armament told another story about design philosophy. The aircraft carried two 7.7mm machine guns, each with 450 rounds, enough ammunition for roughly 45 seconds of continuous fire. American fighters, by contrast, carried far less ammunition, but delivered it through 6 or 8 50-caliber weapons, generating 5 times the destructive force in every second of combat. The implication was clear. Japanese pilots needed to be deadly marksmen because they couldn't rely on overwhelming firepower. Testing of the Nakajima engine revealed something that contradicted everything Allied intelligence believed about Japanese manufacturing. Cylinder tolerances were actually tighter than American specifications, and metallurgical analysis showed alloy compositions suggesting access to strategic materials that intelligence experts insisted Japan simply didn't possess. The power plant produced 925 horsepower through supercharging methods that rivaled or exceeded American designs. Here was an industrial capability hiding in plain sight. Range testing provided crucial insight into Japanese operational planning. With 158 gallons of internal fuel capacity, the Oscar could maintain a combat radius of approximately 400 miles, sufficient for homeland defense but wholly inadequate for the long-range escort missions increasingly demanded of Allied fighters. Drop tanks could extend that range beyond 800 miles, but only by sacrificing the aircraft's most dangerous quality, its agility. It was a trade-off that defined the aircraft's entire purpose. Direct comparisons with Allied fighters proved illuminating. Against the P-40 Warhawk, the Oscar dominated absolutely in climb rate, turning radius, and low-speed performance. Yet the Warhawk possessed superior diving speed, structural durability, and concentrated firepower that could neutralize those advantages if exploited intelligently. Against the newer P-51 Mustang, the disparity became overwhelming. The Mustang's speed advantage was so dramatic that it could attack or retreat completely at will, rendering the Oscar's legendary turning ability tactically irrelevant. Interviews with captured Japanese pilots, conducted through interpreters at testing facilities, unveiled training methods starkly different from Allied practice. Japanese aviators received approximately 400 hours of type-specific training before combat deployment, nearly double the preparation given to American pilots. This intensive preparation appeared necessary because safely exploiting the aircraft's performance envelope demanded exceptional pilot skill. One mistake, one miscalculation of structural limits could prove fatal. The pilots discussed their aircraft's shortcomings with striking candor. They understood precisely what their fighters couldn't do and had developed tactical doctrine to minimize those vulnerabilities. Standard procedure emphasized climbing attacks that exploited the Oscar's vertical performance, followed by immediate disengagement before American firepower could make contact. Sustained dogfighting was avoided unless Japanese pilots possessed overwhelming numerical advantage or altitude superiority. It was a doctrine born from clear-eyed understanding of capability and limitation. By November, comprehensive analysis culminated in a classified report that reshuffled Allied understanding of Japanese air power. The Oscar embodied a coherent design philosophy: prioritize pilot skill over airframe durability, creating a weapon that excelled in the hands of experienced aviators but became catastrophically vulnerable to replacement pilots lacking proper training. The aircraft's maneuverability was genuine, yet it came at the cost of structural margins that Western engineers considered non-negotiable for combat survival. The final conclusion was blunt. Japanese fighter design represented brilliant engineering, constrained by resource limitations and cultural values. But those constraints created fundamental vulnerabilities that could be systematically exploited. The Oscar could outturn any Allied fighter, but it couldn't outrun them, couldn't outdive them, and couldn't absorb the battle damage that American aircraft routinely survived. As the war entered new phases where Japanese training advantages eroded and American industrial capacity increasingly determined outcomes, understanding these limitations became strategically crucial. Classified tactical bulletins began circulating to frontline squadrons in early 1944, detailing technical findings from the testing programs. Captain James Watkins of the 9th Fighter Squadron received his copy of Technical Intelligence Bulletin 47 on March 15th, while his P-38 Lightning unit operated from Dobodura Airfield in New Guinea. The document's clinical language couldn't disguise its revolutionary implications. For the first time, Allied pilots possessed systematic knowledge of their most formidable adversary. Watkins had lost 3 wingmen to Japanese fighters on previous tours, losses he'd attributed to impossible maneuverability that no Allied aircraft could match. The new intelligence revealed the truth. Those miraculous turns came with structural consequences that changed everything about how the war could be fought. The tactical doctrine shift began with fundamental philosophical change. Rather than matching Japanese turning ability, Allied pilots should exploit their aircraft's superior diving speed and structural strength. The engagement should be fast, brutal, and brief. Fire concentrated bursts, then immediately withdraw before Japanese pilots could respond with their characteristic turning maneuvers. The P-38's twin engines provided both the speed required for these tactics and the concentrated nose-mounted firepower necessary for quick kills in brief combat windows. Watkins first applied this doctrine during a patrol over Wewak Gulf on August 2, 1944. His flight formation encountered 12 Japanese fighters at 15,000 feet, odds that would have been disastrous under traditional fighting doctrine. Instead of accepting turning combat, Watkins led his formation in a high-speed diving attack that incorporated every advantage the testing had identified. The Lightnings dove through the Japanese formation at over 400 miles per hour, each pilot delivering 2-second bursts from their concentrated armament. The results vindicated months of analytical work. Watkins destroyed 2 Oscars during that initial pass, watching both aircraft disintegrate under the concentrated fire from multiple caliber weapons and cannon. His wingman, Lieutenant Robert Chen, scored hits on a 3rd Oscar that immediately trailed smoke and began losing altitude. Most significantly, the Japanese formation's attempts to respond through tight turning maneuvers only demonstrated their inability to engage fast-moving opponents, refusing conventional dogfighting. The most revealing moment came when the remaining Japanese fighters attempted to climb back to altitude following the Lightning formation's initial attack. 3 Oscars pushed their engines to maximum power in steep climbing turns, exactly the tactical response the testing had predicted. At approximately 4,000 feet per minute climb rate, 2 of the 3 Japanese aircraft experienced what appeared to be structural failure. Their wings folded upward in the characteristic pattern, indicating G-force loading beyond design specifications. Chen watched 1 Oscar attempt a maximum rate climbing turn, only to have its port wing separate completely from the fuselage, the aircraft tumbling into an uncontrollable descent while the pilot struggled unsuccessfully to escape the disintegrating airframe. It was precisely the structural failure that testing had identified as inevitable when Japanese pilots exceeded carefully calculated performance boundaries. The engagement's success spread rapidly through Allied fighter squadrons as pilots shared intelligence about effective tactics. The 58th Fighter Group in China applied similar hit-and-run methods against Japanese formations over the Yangtze River Valley, achieving kill ratios that reversed earlier trends. British Spitfire units in Burma adapted the doctrine to their aircraft's capabilities, using superior diving speed to offset the Oscar's turning advantages. Australian P-40 units in the Southwest Pacific discovered they could finally engage Japanese fighters on favorable terms by refusing turning combat and systematically exploiting structural limitations. The intelligence proved equally valuable for training replacement pilots who no longer faced the psychological burden of fighting an apparently invincible enemy. Flight schools in the United States began teaching specific anti-Oscar tactics, emphasizing speed and firepower over traditional aerial combat maneuvers. New pilots arrived in combat theaters with systematic knowledge of Japanese capabilities and limitations, rather than the folklore and speculation that had characterized earlier training. By late 1944, the tactical revolution was producing measurable results throughout Pacific combat zones. Japanese Oscar units that had previously achieved 3 or 4 to 1 kill ratios struggled to achieve parity against Allied formations refusing to fight on Japanese terms. The 64th Sentai, one of the Imperial Japanese Army Air Force's most experienced Oscar units, reported losing 17 aircraft while claiming 25 Allied fighters during October and November operations over the Philippines, a ratio representing tactical defeat for a unit that depended on efficiency to offset industrial disadvantage. The psychological impact became apparent through intercepted radio transmissions and captured documents. Veteran pilots who had dominated Pacific skies during 1942 and 43 found themselves unable to exploit their aircraft's legendary maneuverability against opponents who understood and avoided Japanese tactical strengths. Replacement pilots, lacking the extensive training earlier Japanese aviators had received, proved catastrophically vulnerable to Allied pilots systematically exploiting Oscar structural limitations through proper tactical application. The most tragic confirmation came through Japanese training accidents mirroring combat structural failures. Flight schools in Japan reported increasing numbers of training aircraft lost to wing failures during advanced maneuvering exercises. Inexperienced pilots attempting to duplicate the tight-turning maneuvers that had made the Oscar legendary pushed lightweight airframes beyond structural limits that veteran pilots had learned to respect through years of careful experience. Intelligence from captured Japanese maintenance personnel revealed growing awareness within enemy units that their aircraft's greatest tactical advantages were becoming liabilities under changing combat conditions. Ground crews reported increased structural inspections and reduced authorized G loading limits that effectively neutralized much of the Oscar's performance envelope. The same design philosophy that had created Japan's early air superiority was adapting poorly to prolonged combat against opponents who understood its fundamental weaknesses. The intelligence revolution, beginning with Lieutenant Gessel's wreckage analysis at Bona Airfield, had fundamentally altered tactical balance in Pacific air combat, transforming the mysterious Oscar from invincible opponent into a well-understood enemy whose capabilities and vulnerabilities could be systematically exploited through proper application of Allied technological advantages.